Alright, so last time we learned about a new approximation tool that mathematicians and more importantly physicists use all the time. What was this approximation tool? Taylor polynomials, exactly. So what necessary information did we have to have in order to use the Taylor polynomial, or the infinite series approximation? We needed to have something and essentially an infinite number of different forms of it. So we need to have a function, right? Okay, so we have a function, and then we also need to know how to do, what do we do to that function in the
Derivatives.
derivatives, right. So we have a function, we can take any number of derivatives that we want, and in this Taylor series, of course, the more derivatives that we take, the more accurate this approximation tool becomes. So it's like we said, at the end of the day, the value of this polynomial approximation is that you can use it to calculate values of functions that are either impossible to calculate by conventional means or that are just too difficult at any one time. Does anybody remember the example that I gave, or I think we might have done a couple of examples in class, where a Taylor approximation would be a value? What kind of functions?
Function is 0 equals 1. First derivative of the function is 0 equals -2. Keeps going.
So, wait, what do you like? What is the function there? What are you looking at?
Our example says function of 0 equals 1.
Oh, okay, I know what you're talking about. Okay, so that was how we were building up to the Taylor series. Yeah. A fine example might be wave functions like sine, cosine, tangent. As you know, if I said find the sine of 15 right now, you probably need a calculator, unless you had this approximation tool now. You can do it that way. But you would need a calculator otherwise. Exponential functions. Those are other tough ones to work with. You would need a calculator, or the Taylor series, of course, to circumvent that and find the value for some x that we're looking for. All right, let's look at our homework problems that we had. And I have here our first one. Wanted us to find the first three Taylor polynomials and graphs of, was it f of x equals e to the x. And it wanted it at x equals 0. Did anybody have any luck with this one? I know I've read it yet. Anybody else? How many who found this one to be difficult? I'm just curious. Kind of difficult. Okay, that's fine. That's why we're reviewing them. All right. So the first thing we should know is that when we are looking at this function e to the x, f of 0, so if we plug 0 in here, is going to be equal to f prime of 0 is equal to f double prime of 0, and even the third derivative, and we could go on forever. Now why can I say that the original function at 0 is equal to its derivatives at 0? In other words, what is special about f of x equals e to the x, for those of you that are in calculus? I'll rephrase it actually. What's the derivative of this function?
X to the x e to the x minus 1. X e to the x.
Well, this is a special function. And you may not know this actually. Okay, so you're learning an additional something right here. If we take the derivative of e to the x, it's simply e to the x. And if we take the second derivative, it's again e to the x. It does not change. So, obviously, if we put in 0 in both the original function and its derivative, they're going to be the same because they equal the same thing. So f of 0 is equal to the first derivative is at 0, the second derivative at 0, third derivative, and so on until infinity. The infinite derivative at 0 is going to be the
So
same.
it only works when x equals 0.
No, it could be any number, but remember we use, or were you here? You weren't here, okay. Well, when we do a Taylor approximation, we use, when we're relating to what we have here, we use that into our function, we plug that in. You'll see in a second if you weren't here. All of these then will equal e to the 0, which is simply equal to what? What's any function to the 0? What's that?
1.
1, right. Excellent. Excellent. Not yet. Not yet. Now, of course, our form for our approximation, we're looking at any number of polynomials. That's what the n here stands for. The general form is the function at 0 in this case, since that's what we were asked. F of 0 plus prime of 0 over 1 factorial times x plus the second derivative at 0 over 2 factorial times x squared. And we could go on and on and on with this. And that is our format when we're not looking at the function or when we're not approximating at some new value. This is the form that we use. And see, now you see why we were concerned with all the f of 0, f prime of 0, and so on, because that's what we use when we're looking at our original given statement up here. We'll put in the 0 in that place. Okay, so that's our form. So if we go back and we look at each polynomial, so if we're looking at our first one, what would our first polynomial be? Using this form. So I'll give you a hint. Our first polynomial will end right here since we go to the first degree term of x here. 1 plus. So we would have 1 plus, because f of 0 as we know is 1, plus, we know that the first derivative at 0 is also equal to 1, so this would be 1 over 1 factorial x. And if we simplify that, we'll simply get 1 plus x. Not too bad so far. All right, let's do the second one. So as you see here, we are calculating our Taylor polynomials here. We did our first one, now we're doing our second one. So our second one is the same thing as the first, but we include the next term out here. So it would be 1 plus 1 over 1 factorial x plus what? What's our new term now?
Squared over 2 factorials.
Right, so if before we simplify it, it would be 1 over 2 factorial x squared, which becomes 1 plus x squared over 2.
Is that exclamation point too?
Well, 2 factorial is just 2 times 1. So it just 2 times 1 is 2. Just like here, 1 factorial is 1 times 1. So this would just be x over 1, which is just x. Alright, now let's do our third polynomial. We'll have 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus what? What's our new term?
1 over 3 factorial x cubed.
Very good. And of course, 3 factorial is 3 times 2 times 1, which is 6. All right, so the first part of this problem is done. We found our first 3 Taylor polynomials. Now let's look at the graphs. And to do so, I'm going to create some board space over here. And I think when we consider the graphs, this is when you'll really see the Taylor polynomials take off and why they work, why they help you. Because this right here, and unless you are a excellent math brain kind of person, which that's something that sometimes you even have to train to be, it's hard to see why exactly these are increasingly better approximations for our function that we want. That's hard to do. But when we look at the graphs, I think it'll become clear. So let's look at our first polynomial. For comparison, we'll put our original function in there. And we'll just have negative positive 1 here. E to the x looks a little something like that. So there's y equals e to the x. If we graph y equals 1 plus x by comparison, we'll find it looks something like that. So there's our first graph. I'll give you a second to get that down.
Can I use the checkers?
Alright, let's analyze this before we move on to the second one. This first approximation, so we were only looking to the first power of x, really is only close to this function right in this area. So if we're trying to look at a value farther away than anything in here, this approximation becomes less and less efficient. The gap between the original function and our approximation is getting bigger and bigger and bigger, making this approximation worse and worse and worse and worse. So let's see why taking it up a notch to higher powers makes it better. I should have room here. So this is our second approximation. So again, we'll note our original function, something like that. Now if you have your graphing calculator, And actually, let's change this end a little bit, because we can expand our view here and see why it's even a little bit better. E to the x actually looks something like this. If we're graphing our second approximation here, it looks a little something like that. So as you can see here, this second approximation hugs this original function for a bigger area in here. If I could draw with 100% accuracy, you might even see that a little bit better. But we're getting closer. This function looks more like e to the x than our first approximation, which was just a straight line. So now we're actually starting to match up curves here, even better. And now our third graph. There's y equals e to the x. And if we plot our third approximation, we have that there. Now we notice that the difference between these two is marginal for a much greater period of time than our original first degree approximation over there. This is much better. So imagine if we carry this out now to the fourth or fifth or sixth term in our Taylor series. This is going to follow it much closer for a much greater bit of the original function. Any questions on this first one? Yes, this is for number one. So we calculated our first three Taylor polynomials and we graphed them. And all I did was I added in here the comparison to the original function. So you can see why each one becomes better as we go to higher degrees of approximation.
Do we have to do that?
For number one,
I mean, do we have to show
the original function? No. I think it just gives it some value for comparison. Because that's what it's all about. It's approximation to the original function. All right. All right, let's look at number two. 2 wanted to determine the nth polynomial of f of x equals 1 over x at, again, x equals. All right, first step is to get our derivatives down. So our function is 1 over x, which is the same thing as x to the negative first power. What would our first derivative be?
would say like negative x to the negative 1
Minus 2.
Yeah, yeah, you're right. Yeah,
So this is a normal derivative.
How come the last one wasn't normal?
Yeah.
the last one wasn't normal.
No, like they were all the same thing.
That's just how e to the x works. It's actually one of those nice ones that you ever see it on a test and someone wants you to calculate derivatives. You're
So
done.
it's not nothing
You
with
already
Taylor
know.
polynomials, it's just like
It's
that
just how it
specific
is.
derivative.
It's just that specific
But like
derivative.
this one we can do normal.
The rest
Yep.
of them will be like normal derivatives.
Yep, you're probably aware of some functions, I would think, from calculus that are a bit unusual that you have to memorize because their derivatives don't follow the same pattern as using like the
Probably.
power rule here.
Probably.
E to the x is one of them. It just stays the same, stays
Okay.
itself. There's like a whole long proof you could do to show that.
I'm sure.
Just, it's easier to memorize
But
than
this
to-
one is like
to do
normal
that.
then.
Yes, yeah. Alright, so the second derivative, and what we're doing here, we're just establishing a pattern so that we can see what the nth derivative might be because we'll use that for the nth polynomial term. Alright, so what's our second derivative?
2x to the negative third.
Alright, I'm just going to write it as, since bringing it down front, negative 2 times negative 1 x to the negative third. Our third derivative would be what?
Negative 6x to the negative 4.
Excellent. And I'm just going to keep writing it out in the long form. Like that. Do we see a pattern forming here?
Yeah, I see the pattern.
So really what we have here is a negative factorial of n, whichever we're looking at, that's going to be our nth term. Just like if I said, what would be, for the third term here, we would have negative 3 times negative 2 times negative 1. That's a factorial there. X to whatever that number is, 1 smaller. Now we can write that down. We can do that. Because that's what the problem's really asking. With one exception. It wants it at x equals 0. So what happens if we put in 0 for x here? It does not exist, right? Right? So that means our nth polynomial does not exist for x equals 0.
When x equals 0, you can put like 1 over x equals 0.
Because you would have 0 in your denominator. Yeah, so if you plot 1 over x, you'll see of course that it never has a 0 value for x. Because function doesn't exist there. So our nth polynomial at x equals 0 also does not exist. Because there's no slope there if there's no function there. It doesn't work. So that was kind of a trick question, I don't know if you want to think of it that way, but really what it did is it was testing your ability to find derivatives, see the pattern, and then go, oh wait, no matter what degree that we take this to, at x equals 0, it's always not going to exist. So you're just getting familiar with it. Getting better and better. Alright, so for our last one, we're really giving a specific example, and we're putting this into full swing now. So for number 3 wanted the second. So, second Taylor polynomial at x equals 1 this time to approximate the square root of 1.02 using f of x is equal to the square root of x. Alright, so what should my first step be? What did I do in that last one? I started with the function and then did what? Did the derivatives. We're going to do the exact same thing, only we're going to consider it at f of 1 instead, because that's what we're looking at instead of at x equals 0, because remember we did f of 0, because that's what we were basing it around. This time we're basing it around the 1 position for x. So our function originally is the square root of x, can also be written as x to the 1/2 power. So when we look at f of 1 then, we get what? 1. Very good. 1 to the 1/2 is still 1. So our first derivative becomes,
So 1/2.
what's just the general form here?
1/2 x to the 1/2 minus 1.
So we have
To the
1/2
-1/2
x
to the negative.
to the negative 1/2, right? Because 1/2 minus 1 is negative 1/2. First derivative at 1, so plug in 1 here for x, what are we going to get?
1 there.
Well, if we put in 1 here for x, we'll essentially have 1 over the square root of 1, which is 1. So 1 times 1/2 is just 1/2. Second derivative is what?
1.
Negative 1/4, very good.
X to the negative 3/2.
X to the negative 3 has excellent. All of you are doing great. Alright, so the second derivative at 1. Negative 1/4. Very good. Very good. Alright, so let's plug this into our Taylor polynomial approximation equation. Only usually where we have the f of zeros, whether it's the original function or the derivatives, we're going to put in the values here that we just assigned for 1. And of course we only went this far because it only asked for our second Taylor polynomial. And taking it out to our second derivative is our second Taylor polynomial. Alright, so put a little more chalk here first. And we'll do our approximation here. So our second Taylor polynomial approximation is, first term, it's just our original function at the value that we're looking at it.
1.
So it's just 1 plus, we're going to have 1/2, where f prime of 0 usually is, but we have f prime of 1 this time, over 1 factorial times x. Now here's one small change. One small change. Since we're looking at it at 1, rather than having just x, we're going to have x minus 1. So that'll be our term in there from now on. That'll be the whole term that will square or cube or whatever power you wanted to take it to, because we're not doing it at 0. And this doesn't violate the same form that we've had. If we were using it at x equals 0 in the past, x minus 0 is just x. So this is really the true form for any value other than doing it at x equals 0.
So because x is 1, you have to like make an equation that makes x equal
Yeah.
1? Is that right?
You mean,
Like if I set that equal to 0, then like I'd get x equals 1. Is that why you said x minus 1?
that's a very good question. But no, because you're looking at, this is constituting the change here. This is the change between whatever value x is and the one point that we're actually examining at. So if we go farther away, if we increase x, this change is going to be bigger. And it's going to make this polynomial be less effective if we're at values that are far away.
So it's just minus one because x equals one?
Yes, yeah.
The actual.
If this was x equals 0, this would be x minus 0, which would just be x like we've been doing
So x
before.
5 would be x minus 1.
You got it, you got it. Sometimes you'll see this as being labeled your a term, and the form would be x minus a.
Why don't they just make that all 0? Like if you're getting it to 0 anyway, why don't they just make it times 0?
Instead of 1 here?
Instead of minus, like, it's like essentially saying x minus x, which is 0.
Well, it just hold on a sec, you'll see. You'll see, because x here is going to change.
Okay.
Okay. Because x here is the value that we're maybe trying to approximate, which is the kind of the next part of our equation here. Okay, so let's keep building on this. Then we'll have minus 1/4 over 2 factorial x minus 1 squared. So we've taken it out to our second term now. All right, so this is our second Taylor polynomial in x equals 1. We'll want to use this to approximate now the square root of 1.02. Now, if we put 1.02 here in the position of f of x, we'll get a value that is very similar to when we put 1 in for x. Because the square root of 1 is 1, and the square root of 1.02 probably isn't going to be that much different than 1, producing an answer that's 1. So that's why we had to look at our polynomial at this position, because we were going to approximate a value that was very close to it. Remember how in problem 1 I said if we look at values that are farther away from that range where they overlap, where the function, it becomes less accurate? That's because we would have to go back and we would have to change what value we're examining the function at so we can make it closer to those higher values. So if we were looking at, say this wasn't a square root and we just wanted a function at like 10 or something like that, we want to go back and look at a number here that was closer to that value originally. Now, 10 wouldn't be great because that's an easy one to do, and these approximations are for difficult